The engineer is correct. Table 310.15b2 only applies when multiple conductors are carrying current simultaneously. For motors that are mechanically interlocked from running simultaneously or two-speed motors, the conductors for each motor or motor winding do not have to be derated because they will not be carrying current at the same time. This is confirmed by the 2017 NEC commentary on Table 310.15b2 conductors derated if part of same circuit. The second set of notes applies to conductors that are part of the same circuit, but not necessarily carrying load current simultaneously. Examples of such conductors include conductors from a common neutral bus to three-wire branch circuits, or conductors in a motor circuit having two hot legs and a single neutral. Conductors in such circuits are not subject to the provisions of this table because overcurrent protection for conductors in such circuits is provided for by other provisions of the code, such as 430.32b. The exception to this rule is if the conductors are in a raceway or cable with other conductors that are carrying current simultaneously. In this case, the conductors for the motors that are not carrying current simultaneously must still be derated according to Table 310.15b2. The reason why the conductors for motors that are not carrying current simultaneously do not have to be derated is because the overcurrent protection for these conductors is provided by other provisions of the NEC, such as 430.32b. This section requires that motors be protected against overcurrent by one of the following methods: firstly, a separate overcurrent device for each motor; secondly, a single overcurrent device for a group of motors, provided that the overcurrent device is rated for the sum of the currents of the motors in the group; thirdly, a branch circuit overcurrent device, provided that the overcurrent device is rated for the sum of the currents of the motors and the other loads on the branch circuit. In the case of motors that are mechanically interlocked from running simultaneously, or two-speed motors, the overcurrent protection is provided by a single overcurrent device for the group of motors. This overcurrent device is rated for the sum of the currents of the motors in the group, but it will only trip if all of the motors in the group are running simultaneously. Therefore, the conductors for the motors that are not carrying current simultaneously do not need to be derated. To elaborate further, let's break down the concepts and NEC sections involved. Firstly, conductor ampacity refers to the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor is determined by factors such as its size, insulation type, and the ambient temperature in which it is installed. Secondly, derating factors are adjustments applied to the ampacity of conductors when multiple current-carrying conductors are bundled together in a raceway, cable, or directly buried in the earth. These factors reduce the allowable ampacity to prevent overheating of the conductors due to the combined heat generated by all the conductors. Thirdly, NEC Table 310.15b2 provides the derating factors for conductors based on the number of current-carrying conductors in a raceway or cable. The table specifies the percentage of ampacity that the conductors can carry based on the number of conductors. For example, if there are 4 to 6 current-carrying conductors, the ampacity is derated to 80% of its original value. The key here is the phrase current-carrying conductors. The derating factors in Table 310.15b2 are only applicable to conductors that are carrying current simultaneously. If conductors are part of a circuit but do not carry current at the same time, they do not need to be derated according to this table, unless they are in a raceway or cable with other conductors that do carry current simultaneously. Article 430 of the NEC covers motors, motor circuits, and motor controllers. It provides specific requirements for the protection of motor circuits, including overcurrent protection. Section 430.32b specifically addresses motor overload protection. This section mandates that motors be protected against overcurrent by one of 3 methods. Firstly, a separate overcurrent device for each motor. Secondly, a single overcurrent device for a group of motors, provided that the overcurrent device is rated for the sum of the currents of the motors in the group. Thirdly, a branch circuit overcurrent device, provided that the overcurrent device is rated for the sum of the currents of the motors and the other loads on the branch circuit. In the case of motors that are mechanically interlocked or two-speed motors, The overcurrent protection is typically provided by a single overcurrent device for the group of motors. This device is rated to protect the entire group, but will only trip if the total current exceeds its rating. Because the motors do not operate simultaneously, the conductors for each motor do not need to be derated as if they were all carrying current at the same time. Let's consider an example of two motors that are mechanically interlocked. This means that only one motor can operate at any given time. Suppose each motor has a full load current of 20 amps. If the motors were to operate simultaneously, the conductors would need to be sized to carry a combined current of 40 amps, and derating factors might apply if there are multiple conductors in the same raceway. However, since only one motor operates at a time, the conductors only need to be sized to carry the current of a single motor, which is 20 amps. Therefore, derating factors from table 310.15b2 do not apply unless these conductors are in a raceway with other conductors that do carry current simultaneously. Now, let's consider a two-speed motor. These motors have two different windings that allow them to operate at two different speeds. Only one winding is energized at a time. Similar to the mechanically interlocked motors, the conductors for each winding do not need to be derated as if they were carrying current simultaneously. The conductors only need to be sized to carry the current of the winding that is energized. This is because the overcurrent protection, as per 430.32b, is designed to protect the motor based on its operating condition. However, it is crucial to note that if the conductors for these motors are run in the same raceway or cable as other conductors that are carrying current simultaneously, the derating factors from table 310.15b2 will apply. In this case, all current-carrying conductors in the raceway or cable must be considered when applying the derating factors. It is also important to consider other factors that can affect conductor ampacity, such as ambient temperature and the presence of other heat-generating equipment. These factors can require additional derating of the conductors to ensure that they do not exceed the temperature rating. Ambient temperature correction factors are applied when the ambient temperature around the conductor is higher than the temperature for which the conductor's ampacity is rated. These factors reduce the allowable ampacity of the conductor to account for the increased heat. Furthermore, continuous loads are defined as loads that operate for 3 hours or more at a time. For continuous loads, the conductors must be sized to carry 125% of the continuous load current. This is to prevent the conductors from overheating due to the extended period of operation. To summarize, when dealing with motors that are mechanically interlocked or two-speed motors, the conductors for each motor or motor winding do not need to be derated according to table 310.15b2 or if they do not carry current simultaneously. However, if these conductors are in a raceway or cable with other conductors that are carrying current simultaneously, the derating factors will apply. Additionally, other factors such as ambient temperature and continuous loads must be considered when determining the appropriate conductor size. It is always recommended to consult the latest edition of the NEC and to seek guidance from a qualified electrical engineer or inspector when designing and installing electrical systems. The NEC provides specific requirements for the protection of motor circuits, and it is important to follow these requirements to ensure the safety and reliability of the electrical system. Understanding these principles helps in designing safer and more efficient electrical systems for motor applications. Moreover, it is beneficial to further clarify the different aspects of motor conductor sizing and protection. Firstly, let's delve deeper into the concept of mechanically interlocked motors. Mechanical interlocking ensures that only one motor can operate at any given time. This is typically achieved through mechanical linkages or electrical controls that prevent the simultaneous operation of multiple motors. For example, in a system with two pumps where only one pump is needed at a time, a mechanical interlock ensures that only one pump can run, preventing overload and potential damage. Secondly, when considering two-speed motors, it is essential to understand how the different windings are configured. Two-speed motors typically have two separate windings, each designed for a specific speed. Only one winding is energized at a time, and the motor's control system ensures that the appropriate winding is activated based on the desired speed. Because only one winding operates at a time, the conductors supplying each winding do not need to be sized as if they were carrying current simultaneously. Thirdly, the exception regarding conductors in a raceway with other current-carrying conductors is crucial. If the conductors for motors that do not operate simultaneously or run in the same raceway are capable as other conductors that do carry current simultaneously, the heat generated by all the conductors in the raceway can cause overheating. In this case, the Derating factors from Table 310.15b2 must be applied to all conductors in the raceway, including those that do not operate simultaneously. Fourthly, NEC Section 430.22 provides specific requirements for the minimum ampacity of motor circuit conductors. This section states that the conductors supplying a single motor must have an ampacity not less than 125% of the motor's full load current. This ensures that the conductors can handle the motor starting and running currents without overheating. For example, if a motor has a full load current of 20 amps, the conductors supplying the motor must have an ampacity of at least 25 amps, which is 1.25 times 20 amps. Fifthly, NEC Section 430.24 addresses the sizing of conductors supplying multiple motors. If two or more motors are supplied by a single set of conductors, the conductors must have an ampacity not less than the sum of the full load currents of all the motors, plus 25% of the full load current of the largest motor in the group. This requirement ensures that the conductors can handle the combined current of all the motors, with an additional margin for the largest motor. Sixthly, ambient temperature correction factors are used to adjust the ampacity of conductors based on the ambient temperature in which they are installed. If the ambient temperature is higher than the temperature for which the conductor's ampacity is rated, the conductor's ampacity must be reduced to prevent overheating. The correction factors are typically provided in tables in the NEC. Seventhly, continuous loads are defined as loads that operate for 3 hours or more at a time. For continuous loads, the conductors must be sized to carry 125% of the continuous load current. This requirement is in addition to the requirements for motor circuit conductors and ensures that the conductors can handle the continuous load without overheating. Eighthly, it is important to consider the type of insulation used on the conductors. Different types of insulation have different temperature ratings, which affect the ampacity of the conductors. The NEC provides tables that specify the allowable ampacity of conductors based on their insulation type and temperature rating. Ninthly, the overcurrent protection for motor circuits must be sized to protect the conductors and the motor from overloads and short circuits. The overcurrent protection can be provided by fuses, circuit breakers, or other overcurrent devices. The size of the overcurrent protection device must be coordinated with the ampacity of the conductors and the full load current of the motor. Tenthly, when installing conductors in raceways, it is important to consider the full capacity of the raceway. The NEC specifies the maximum number of conductors that can be installed in a raceway based on the size of the raceway and the size of the conductors. Exceeding the full capacity of the raceway can cause overheating of the conductors and can also make it difficult to pull the conductors through the raceway. In summary, when dealing with motor circuits, it is essential to carefully consider all the applicable requirements of the NEC, including the requirements for conductor ampacity, derating factors, overcurrent protection, and raceway fill. By following these requirements, you can ensure that the motor circuit is safe and reliable. Additionally, understanding the specific characteristics of the motor installation, such as whether the motors are mechanically interlocked or two-speed, and whether the conductors are run in the same raceway as other current-carrying conductors, is crucial for determining the appropriate conductor size and protection. Always consult the latest edition of the NEC and seek guidance from a qualified electrical professional when designing and installing motor circuits. This comprehensive approach ensures compliance with safety standards and optimal performance of the electrical system. Finally, ensure you are using the proper wiring methods. Proper wiring methods include using appropriate conduit types, ensuring proper termination of conductors, and providing adequate support for the wiring system. Different environments may require different wiring methods. For instance, wet locations require specific types of conduit and fittings to prevent water from entering the system. Similarly, hazardous locations require explosion-proof wiring methods to prevent ignition of flammable materials. Attention to detail in wiring methods ensures the long-term reliability and safety of the electrical system. Regular inspections and maintenance are also crucial for identifying and addressing any potential issues before they become major problems. This proactive approach helps to ensure the continued safe and efficient operation of the electrical system.